righty, howdy folks. Good to see you guys back here. We're going to spend another day dealing with trig form of complex numbers. So just a little recap. Again, this is something that we actually did already last class, but just kind of recap it again. And also kind of go over some of the terminology that we haven't really had a chance to, didn't really get into the last class or last video. So we have this idea that R cis theta, and cis is short for cosine I sine. So the trig form of a complex number. We said that R is the absolute value of Z, but it actually has a specific name. We actually want to call it the modulus. So R is the modulus, and it's represented by the absolute value of Z. And theta is more than just the angle of the complex number. It's what we call the argument. So again, same kind of deal that we were looking at when we were dealing with vectors. It's just we've just changed the names a little bit, but still R and theta. So again, just to remember, when we're multiplying two complex numbers together, all we're doing is multiplying the R values and adding the angles. So we end up with 9 times 4. Cosine, or cis, cosine I sine, 2 pi over 3. That's not a pi. Whoop. There we go. 2 pi over 3 plus 17 pi over 6. So when we multiply that all the way out, we end up with 36 cis. And again, we did this problem yesterday. So it's just a little review to make sure we're all kind of on the same page before we dive into things. Plus 17 pi over 6. And that'd be 36 cis 21 pi over 6. And we're multiplying the numbers together, or 36 cis 7 pi over 2. And if we're dividing the numbers, we said that's the same thing as dividing the moduli, the modulus of each complex number, and then subtracting the arguments or subtracting the angles. So that'd be 9 divided by 4, cis 2 pi over 3 minus 17 pi over 6. So we already talked about multiplication and division, just to kind of get our heads screwed around again, that we're dealing with some more operations of complex numbers, and that would end up being negative 13 pi over 6. But if we, let's go back to that idea of multiplication. If we were to continue doing it over and over again and deal with repeated multiplication, well, then we would get into this idea of exponents, which again is nothing new to us. So if we were to get into this idea of exponents and repeated multiplication, we would end up with right here where we just kind of multiply and multiply and multiply. And what happens there is you end up finding this little pattern. And a French mathematician named Abraham DeMoivre's kind of noticed this pattern. And it basically, when you do this over and over again, it's the same thing as taking the modulus to an exponent and then multiplying the argument or the angle by that exponent. So we can raise any number to an exponent. We can raise any complex number to an exponent. So how would this work? Say I'm looking at a number kind of like this. I'm going to leave DeMoivre's theorem here for us to kind of look at. The first thing we'd have to do is we'd have to be able to turn this into a complex number. So the first thing I want to do is I need to figure out what the modulus is, what absolute value of Z is. So we're going to find out R. So 4 squared plus negative 4 root 3 squared. So that means then that r is the square root of 16 plus 48. So r is the square root of 64. And r would be equal to 8. So we have the r value. And now I need to figure out the argument. So before I look at the argument, I probably better figure out where this number is located at. So it's going to be down here. So it's going to be down in quadrant 3. I'm sorry, quadrant 4. So we have 4 minus 4i root 3. So I need to now figure out the tangent. So tan of this angle is b over a. So negative 4 root 3 over 4. So that means that the argument or the angle is the inverse tangent of negative root 3. So that means it could be 2 pi over 3, or it could be 5 pi over 3. So we learned our unit circle, we got it down. We're kind of looking at where this could be now. And since I'm in quadrant 4, the angle that I want is 5 pi over 3. That's not a pi. So what we're looking at here then is if I'm dealing with 4 minus 4i root 3 to the 9th power, what I'm really looking at here is this idea of z to the 9th power. So I'm going to rewrite this where I take my complex number in standard form and write it in trig form or polar form. So let's write it as 8 cis 5 pi over 3. So I'm using my modulus, my argument to rewrite this. So that means then that z to the 9 is 8 to the 9th. This is what DeMoivre's theorem says. Take the modulus and raise it to that exponent, and then take my angle and I'm going to multiply it by that exponent. And when you do that, z to the 9th is the same thing as 134 million. I do not know this one off the top of my head, so I had to plug this one into my calculator. 217,728 cis 15 pi. And since 15 pi is comparable to just pi, cosine of pi is -1, sine of pi is 0. So if I wanted to, I could go one step further. And I'm not going to make you guys do this, but I could take my number and multiply by -1. Since this is -1 plus 0 pi is 15 pi. So we could go a little bit further if we wanted to, but you don't have to do this. All right, but what I really want to see if you guys can do now is, can you use DeMoivre's theorem to raise an imaginary number to an exponent? So why don't you guys go and pause the video and see what you guys can do. All right, so first things first. You had to figure out what the r value was. So -3 squared plus 3 squared. So r is the square root of 9 plus 9. R is the square root of 18. And I'm okay if you leave it as the square root of 18, or if you wanted to, you could make it as 3 root 2. doesn't really matter. All right, so we got to figure out where this point would be located at. So -3 plus 3i, that's be right up here somewhere. So that means I'm dealing with an angle that's in quadrant 2. So tangent of the angle equals 3 v value divided by the a value. So tangent angle is equal to -1. So theta equals the inverse tangent of -1. Well, this could be located then at 3 pi over 4 or 7 pi over 4. So based upon where this angle is located, we would be dealing with 3 pi, or where this complex number is located, we'd be dealing with 3 pi over 4. So 3 pi over 4 is our argument. So that means that z, so we're going to change the form real quick. So z is going to be our r value, and I'm going to use root 18. Cis 3 pi over 4. I know there's some math teachers out there that are probably going, no, not root 18. Make that 3 root 2. Well, it just doesn't matter. So we're going to take this to the 10th power. So we're going to do root 18 to the 10th power. Cis 10 times 3 pi over 4. So if we take root 18 to the 10th power, again, I do not know what that is off the top of my head. So I'm going to plug that into my calculator here. And I ended up with 1,889,568. Cis 30 pi over 4, which is the same thing as 15 pi over 2. So 15 pi over 2, that's equivalent to 3 pi over 2. So that is 0 plus -1i. So if I wanted to, I could make this go a little bit further. You don't have to do this. But if I wanted to, I could go a little bit further, make this -1,889,568i. All right, so this is DeMoivre's theorem when we're raising it to an exponent. But remember, exponents can also be used to represent radicals or roots. So DeMoivre's theorem also can help us be used to help us figure out what a root is. And that's a real funky looking theorem. It looks kind of like this. So let's see if I can't help you guys work our way through this. First thing, whenever you're dealing with this, any sort of imaginary number, even though -8 doesn't look like an imaginary number, it's still a complex number. It helps to figure out where it is on the graph. So we need to know what the modulus and the argument is for this. So -8 plus 0i. So we're going to graph it real quickly, so we know exactly where this thing falls before we actually go through and do it. So -8 plus 0i, that'll be right here. And if it was over there, that means then that r is going to be 8, because 8 units away from the origin. And the argument, well, that'd be at pi. It's on, or 180 degrees. So I'm asking you guys to figure out what is the cube root of -8. So the cube root of z. So if we're dealing with a cube root here, that means then that my n value is 3. So turns out on the complex plane, when we usually do cube roots, where's 1? We'd say the cube root of -8 is 2. But there's actual other numbers that would multiply to give us that cube root on the complex plane if we were to bring it out. And so if you notice, this whole thing is basically just knowing what parts we have and plugging things in. So we have theta, there's our argument, which in this case is pi. R is 8. K, now k is going to be any number from 0 up to n minus 1. So if n is 3, and I know that n is 3 because I'm dealing with the cube root, that means k is any number from 0 up to n minus 1, or 3 minus 1, which is 2. It means there's going to be 3 distinct cube roots to z. So I'm looking for my cube root of z. So that's the cube root of 8, because r is 8. And we're going to be dealing with cosine. The argument, the angle is pi plus 2 pi k all over n, which is all over 3, plus I sine pi plus 2 pi k. And again, I'm not going to go through and prove this one to you, but this is where DeMoivre's theorem really is pretty cool. It allows us to be able to figure out all the distinct complex roots to any number. This is honestly now allows us to kind of get a better appreciation for the fundamental theorem of algebra, because there are multiple roots. Even though that we say that they sometimes have multiplicity, well, they're on the complex plane, those are still distinct roots. So we have this equation. Well, what we're going to do is we're going to end up plugging 0 in for k. So I'm going to plug 0 in for k. I'm going to figure out what each of these distinct roots are. I'm going to plug 1 in for k. I'm even going to go through and plug in 2 for k to figure out what these actual roots are. So my first root, it's this entire thing, but in place of k, I'm plugging in 0. I'm not going to write it all out for you, but I do kind of want you to kind of see how the whole thing ends up working. Sine pi plus 2 pi k, so 2 pi would be a toilet paper, times 0 all over 3. So when I plug this in, I end up with 2 cosine of pi over 3 plus I sine of pi over 3. So now DeMoivre's theorem says if I were to go ahead and raise this entire thing up, I would end up with a number that when I cube it would actually be equal to -8. And that's kind of cool in my mind, because I kind of look at this here and you'll see the number kind of pop out here. An imaginary number that or a complex number that I wouldn't have actually thought of, that when I raise it to the third power, I would get -8. And you guys can actually do that if you wanted to on your calculators. Just plug it in and raise it to the third power, and you'll see that it actually does equal -8. So it's not just -2. Now, one of these other ones will give me -2. I don't know which one will do that, but one of them will still give me -2 because I do know that the cube root of -8 is -2. It's just, usually when we think about these, we don't really think about well, it's not that we don't ever think about the complex numbers that also would have given us that same root. Because each root is distinct. It's just when we look at our normal graphs and our normal values, we don't think about the complex plane. We think everything in terms of the real number line and the XY axis. So we plug everything in here. So this time I'm plugging in 1 to get the next root. So if I plug 1 in here, I end up with 2 cosine. That's 3 pi. That would be 3 pi over 3. So 3 pi over 3, that's just pi. Plus I sine 3 pi over 3. So there's my pi again. And cosine of pi is -1. And I sine of pi would be 0. And I end up with -2. So -2 is still a root to -8. It had to be. Just didn't know which one of these k values was going to give me -2. It turns out it was going to be k equals 1. So that means k equals 2 will give me another complex root. So cosine of plus 2 pi. Oh, let's see here. Times 2. All over 3. Plus I sine pi times 2 pi times 2 all over 3. So 2 cosine of 5 pi over 3 plus I sine of 5 pi over 3. Now, sometimes our angles aren't on the unit circle. I'd rather you just leave it than in cis form when that happens. So if they're not on the unit circle where we can get specific numbers for it, I'd rather you just leave it in cis form instead of getting ugly decimal answers. But that's not the case here. These are on the unit circle. Plus I times -√3 over 2 which would be equal to 1 minus I√3. So if you cube 1 minus I√3, that would also give you a number that would be equal to -8. So this is DeMoivre's theorem when it comes to actually determining the roots of a complex number. So why don't you guys go ahead and try one yourselves. Find the fourth root of k equals 16i. All right, let's see how you guys did here. First thing here, I'm dealing with 0 equals z equals 0 plus 16i. So I got to go ahead and graph it. So I can figure out what the modulus and the angle are. So 0, -16i, that'd be, or positive 16i. Oops, wrong way. That'd be up here. So that means my R value is going to be 16. My modulus is 16. My argument, my theta value would be pi over 2. And since I'm looking for the fourth roots, means n is 4. So if n is 4, that means k is going to be every number from 0 up to 4 minus 1. So 0, 1, 2, and 3. And we'll be able to figure out the fourth roots of it. So we're dealing with z equals 16 cis pi over 2. And we're going to figure out what we get when we get k equals 0, k equals 1, k equals 2, and k equals 3. But I just realized I should give myself a little bit more room because I have to first set this up. All righty. So I'm looking for the fourth roots. So the fourth roots of 16 times cosine of theta, so pi over 2, plus 2 pi k all over 4 plus I sine of pi over 2 plus 2 pi k all over 4. So first thing I do is I just multiply all these by 2 here. So that way I don't have fractions inside of fractions. So now all of a sudden I'm noticing that I'm going to have a denominator over 8. And if I have a denominator over 8, there's a very good opportunity that some of my numbers will not be on the unit circle. If they're not on the unit circle, that's okay. I'm just going to leave them in cosine I sine form or cis form. I'm not going to worry about trying to make them, or trying to get decimal answers for them when it doesn't necessarily work out so hot. So cosine plus pi plus 4 pi k all over 8 plus I sine of pi plus 4 pi k all over 8. So here we go. Let's plug them in. Our first root is going to be 2 cosine, whoopsies, of pi plus 4 pi times 0 so that's going to end up being pi over 8. So that's not even going to end up giving me a number that I even like. Which means I'm probably going to do my cis formula from here on out. Times 0. So we end up with 2 cosine of pi over 8 plus I sine of pi over 8. Or better yet, knowing that I'm going to be using cis form, I'll probably leave it as 2 cis pi over 8 from here on out. But these pi over 8's not on the unit circle, so I don't get a real pretty answer here. And again, that's okay. I don't have to. Let me plug it in real quick just so you guys can see what the actual answer would have been if you would have used it. So if I would have taken this further, which I don't recommend, but if I were to have taken this further, this would have been 1.8476. Sine, second pi divided by 8 times 2 plus 0.7654i. So, I mean, I can still plug them in to get a decimal answer if I wanted to. But, friends, there's no reason for that. We'll go ahead and just leave it in sys form. And I got a feeling the rest of these are also going to not be on the unit circle. So, that being the case, that's okay. But as long as we understand what the idea would be, then we're doing pretty well here. So what we're doing here, it's not hard. It's just time consuming. You've got to be organized to make sure that you have everything all set up the right way. So this time we're going to plug 1 in for k. So we have 4 pi, times 1 is 4 pi, plus pi is 5 pi. 5 pi over 8, well again, 5 pi over 8 is not going to be on the unit circle. So I can go ahead and leave that as 5 pi over 8. Looks like I'm counting by pi over 2, so I've got a feeling my next one's probably going to 1 pi to 5 pi. That's 4 pi over 8 more, so I'm probably going to be another 4 pi over 8. So I got a feeling my next one is probably going to be 9 pi over 8. But got to make sure. And that's one of the nice things about this is they will be symmetrical. So once you get your pattern going on your first 2 roots, you'll always kind of have an idea of where it's going from there because it will be symmetrical. So we're going to multiply it by 2. Yeah, and you can see it 4 times 2 is 8 pi plus 1 is 9 pi, so it ends up being 9 pi over 8. And again, these aren't on the unit circle, so I'm just going to leave them in terms of just the trig form, the sys form. I could move it out if I wanted to, but again, no reason to. All right, and then we have our last one. We're multiplying this one by 3. This is where DeMoivre's theorem is really kind of cool. It's this whole idea of being able to figure out the distinct roots. So 4 times 3 is 12, plus 1 is 13, so 2 cis 13 pi over 8. All righty, friends. So today we're just going to take raising complex numbers to a power and also taking the roots of complex numbers. So we'll talk more about this in class. So I'll see you guys then. All right, take care.